Alright, getting on with chapter 9. Start 9.3, simplifying and combining radical expressions. So after reviewing 9.1, which is about radical expressions, and then 9.2, which is rational exponents, we're going to now get to some rules of radicals. First, the product rule for radicals with an example first. So if I have square root of 4 per se times square root of 9, would it be the same answer as 4 times 9 and then square rooting? Let's check. 2, this is 3, 2 times 3, and that's 36. Square root of 36 is 6, so they do equal. So this suggests the rule that says square root of a times square root of b is a times b square root of, and it works actually for any root, not just square rooting. Okay, this is called the product rule. You can go this way, which means timesing and getting the answer, and then or you can split it up by going backwards. Nth root of ab equals nth root of a times nth root of b. So we're going to do forward, and we're also going to do it backward depending on the problem. And there's also what we call the quotient rule for radicals. The quotient rule, same idea. If you have root 4 over root 9, is that the same thing as 4/9 square root? It is. That's 2/3, and that's 2/3. So we say the nth root of a over the nth root of b is the nth root of a over b. As long as you don't divide by 0, again, we can work it out both ways. We've actually used both of these rules earlier without mentioning them. But just be careful, there is no such rule for addition. So square root, say, of a plus b does not necessarily equal root a plus root b. And again, this doesn't work, okay? So simplify. Cube root of 27a cubed over b6. Remember, we did this in our heads. We did it individually because it was times and division. Basically what this means, we're doing the quotient rule, and then on top we're doing the product rule. You don't have to write all this down, but that explains why we could actually do them individually, okay? So you get 3a over b2. You can still do it in one step, but this is just to show you why this is true. Okay, so now when we say simplifying a radical expression, we're going through the steps for that. To simplify a radical expression, it means many things have to be done to simplify a radical expression. The first thing we have to look for is the following. We want to take out the largest perfect square factor if you have a square root. You want to take out the largest perfect cube factor if it's a cube root, and so on. So it really depends on the index, okay? That's what you're going to do first. So let me show you a few examples about that. I'm going to do side-by-side examples. Example 1. Okay, so we all know that square root of 4 is 2. But if we want to simplify square root of 8, if you put that in your calculator, you get a decimal. But 4 is a perfect square factor of 8. So we're going to take it out by using the product rule. 8 is 4 times 2. Using the product rule, we can write root 4 times root 2. That's a 2, so it's 2 root 2. So root 8 is simplified into 2. Let's look at cube roots. We know that cube root of 8 is 2, but if you do cube root of 16, you put it in your calculator, you get a decimal. But we know 16 is 8 times 2. And we use the product rule to split it up. And cube root of 8 is 2. So cube root of 16 is simplified into 2 cube root. So we're taking out the largest perfect cube factor of 16. We took out the largest perfect square factor of 8. Let's do fourth root. We had fourth root of 81, 3, but fourth root of 162 is a decimal, and we know that 81 times 2 is 162. Using the product rule, we split it up. So we're taking out the largest perfect fourth power factor of 162, which is 81. That comes out to be 3, and the answer is 3/4 root of 2. All right, so let's practice more of these. So how do we simplify square root of 128? The first thing I would do is put it in my calculator. If I get a number, I'm done. If I get a decimal, it's not a perfect square. So in order to take out the largest perfect square factor of 128, we gotta divide it by the smallest possible number. Start with a 2 always. Does 2 divide 128 evenly? It is 64 times 2, and I'm splitting it up using the product rule, so that's 8/2, and that's how it's simplified. Square root of 48. Well, 48 is not a perfect square, it's times 24, but I'm not going to use that because 24 is not a perfect square. Then I would go to the next number that divides 48, which is 3. 16 times 3. Does 16 divide? It does, and it's a perfect square. So it's what? 4/3. Let's look at 80. With 80, it's 2 times 40, which is no good. 3 doesn't divide it. 4 times 20 is good, but it's not good enough because 20 is also 4 times 5. So when your number ends with a 0, try 5 first, then 10, then try 2. 5, then 10, then 2. Okay, when it ends with a 0. If you try 5, it's 16 times 5. And that's going to be 4/5. This is a shortcut. If you do 20 times 4, it's going to work eventually. This is also 4 times 5. It's going to be 2 times √5 times 2, which is 4/5. It's more work though. Okay, let's try it with cube root. Again, if you put this in your calculator, cube root of 54, you get a decimal. You start with a 2. 2 times 27 is 27, a perfect cube. When you cube root it, you get 3, so it's 3 cube root of 2. Cube root of -375. Well, 2 doesn't divide it. 3 divides it. 3 times 125. Them has to be negative. I'm always put the negative next to the number that's a perfect cube. So we're going to cube root it separately using the product rule. Cube root of -125 is -5. And then cube root of 3 has to be brought down. So that's the first step in simplifying radical expressions, is to take out the largest perfect square or cube factor depending on the index. Then the second step to simplify a radical expression is no fraction should be left under the radical. And in order to simplify that, you use the quotient rule. Like if you have square root of a over b, you split it up. You're not supposed to have a radical in the fraction under the radical, and then no radical should be left in the denominator. So this is not going to be your final answer. You cannot leave it. What do? We're going to rationalize the denominator. We'll talk about this later. Rationalize the denominator. So this is coming later, okay? All right, so let's simplify look at few examples. Cube root of 4b cubed over 125. While using the product and quotient rules, we can write it as cube root of 4, cube root of b cubed over cube root of 125. 125 is a perfect cube, it's a 5. Cube root of b cubed is b, and 4 is a perfect square, it's no good. So this would be the final answer. Okay. Square root of 75a squared. How do we simplify this? Well, we know a squared is a perfect square. We're going to split it up using the product rule. We know 75 is not a perfect square. 2 doesn't divide it. 3 times 25 is good. 25, okay, a square should be here, sorry. Perfect square should always be up front. So a square and then 25 is a perfect square. 3 is called the leftover. So I split up 75 into 25 times 3. I put the a square with the 25 because it's a perfect square. So it's 5a square root of 3. These are the perfect squares. And this is called the leftover. Okay? Square and leftover. Alright. Here we're assuming all variables are positive. Square root of 147a to the 5th. Well, 147 is not a perfect square, nor is a fifth. So let's do the numbers first. 2 doesn't divide it. 3 times 49. 49 is a perfect square, 3 left over. Although a5 is not a perfect square, but a4 is. So we're going to put the a4 here, and the leftover is a to the 1. Square root of 49 a4 is 7a squared, and then we bring this guy down. Alright, cube root of 40a cubed b6. Well, we're doing cube root, so we're looking for perfect cubes. 40 is not a perfect cube. 2 times 20 is no good. 4 times 10 is no good. 5 times 8, because 8 is a perfect cube, 5 is a leftover. A cube is a perfect cube, so is b6. No leftovers. So that's a 2, a b2, and this guy has to be brought down. Alright, so that's number 5. How do we simplify cube root of 56 a4 b7? Again, we have cube roots. 56 is not a perfect cube. 2 times 28 is not good. 3 doesn't do it. 4, 5, 6, 7, and 8. 8 is a perfect cube. 7 is not. A4 is not a perfect cube, but if we go down one exponent, it's a cubed times a. It's not a perfect cube, but if you go down one exponent, it's b6 times b. So it's 2ab squared, right? Remember, we divide the index into the exponents, and this guy comes down. Okay. This would be number 6. It's the fifth root of 64a6 b10th. 64, if you do fifth root of 64, it's a decimal. 2 times 32 is going to work. So 32 is the fifth power, 2 is the leftover, 6 is not, 5 doesn't divide 6, but it divides 5, so we do a5 times a. 5 divides 10, so we put that with the perfect squares, and that's a 2ab squared, fifth root of 2a. Alright, so that does it for simplifying. Then we have adding and subtracting like radicals. We're still in 9.3. Adding and subtracting like radicals. Okay, let's look at some examples. If we have x plus x, we know 1x plus 1x is 2x's. 1 apple plus 1 apple is 2 apples. But we have x squared plus x, we can't add because the exponents are different. So if we have a root 2 plus root 2, does this look like number 2 or number 1? The indices are the same and the numbers up front, it doesn't have to be, but these are the same. So when the indices are the same and the radicands are the same, it looks like what? The first one, so you do 1 plus 1, which is 2 root 2. 1 apple plus 1 apple is 2 apples. So when can we add radicals? When they are like radicals. And what does that mean? Like radicals, they have same index and same radicand. Same index and same radicand. So this has to be the same, these have to be the same, okay? Like for example, 5 cube root of 7 minus 3 cube root of 7. To be sure, I would box the radical. If they're exactly the same index, same number under radical, then they're like radical, then I would subtract what's up front. That's a 2, and then pull this guy down. You don't change the index, you don't change the number under the radical. Well, sometimes they don't look like radicals, but they are, so you're going to simplify first. Here's an example. Simplify, then combine like radicals. So we're putting two concepts together, like root 8 plus root 32. You can see these don't look like they're like radicals because the 8 is not the same as 32, but if we simplify them using the product rule, you get 2 root 2 plus, this is 16 and 2, so it's 8 root 2. 2 root 2 plus root 2 is 10 root 2. Okay, again simplify, then combine like radicals. Root 80 minus root 128 plus root 288. And 80 is 6 times 5, as we did that earlier. We had earlier 64 times 2 and 144 times 2. So that's 4 root 5 minus 8 root 2 plus 12 root 2. It looks like after simplifying, these two are like radicals, so we pull this guy down, and then we add negative 8 to 12, it's a plus 4, and then we pull down the common radical. Okay, let's do one with cube root. Cube root of 250 minus 4 cube root of 5 plus cube root of 16. Well, 250 is not a perfect cube, but 2 divides it, it's 125, which is a perfect cube. And that's going to be 5 cube root of 2. There's nothing to do on this one. Now this guy can be done 8 and 2. Cube root of 8, cube root of 2, which is 2 cube root of 2. It looks like the two are like 5 plus 2 is 7. Cube root of 2, and this gal would be brought down. Okay. Let's throw in some variables. 2 cube root of 64a plus 2 cube root of 8a. Simplify, then combine like radicals. Well, the 2 is on the outside, it gets pulled down. Now this is going to be a cube root of 64 times cube root of a. 64 is a perfect cube. Cube root of 64 is 4. 4 times 2 is 8. And this guy can be written out as 8 and a. Cube root of 8 is 2. 2 times is 4. And then cube root of a is brought down. Now we have like radicals. 8 plus 4 is 12. Cube root of a is the answer. Okay. Number 5. Square root of 36xy squared plus square root of 49xy squared. Assuming here all variables are positive, So let's do the perfect squares together. 36y squared, the leftover is x. Same thing here, 49y squared, and x is the leftover. Assuming everything is positive, this is 6y root x. This is 7y root x, which is 13y, right? If we add the y's together, so we get 13y root x. Okay, there's a couple more. You can look them over. That's all I wanted to do.